In this video, we are going to solve some of very important past paper questions that are very essential to attempt before attempting your Management 2026 paper. All right, let's start with spring question. A student is determining the spring constant K of a spring by two methods. Figure 1.2 shows how the apparatus is used. Method 1. A. On Fig 1.1, measure the unstretched length L0 of the spring in millimeters. So that is a very important question, like in which a student need to measure the length, and for that should be in millimeters, right? Okay, so that's a very basic issue that students face. Like they get the image, like they get a copy, and then they say that the value that they measured on their paper is not similar to the one that is mentioned in the marks. So what I suggest to my students that do not follow mark scheme exactly, because your printing is different and Cambridge printing is different. So whenever you have to attempt the same kind of question in Cambridge, uh, you will be getting the same answer as like that in the marks. Okay. So if we go with the mark scheme, that is about 22. But if we go according to my image right now, so this is 1.8 or 18. Okay. But uh, just let me give you another example. Like, see, look at me here. I am improving the size of the image. Okay. Then you can see that now the value has been changed to 1.9. Okay. So it depends on the print size, like the print that you are taking. For example, for now, if I leave it to the one that we have already discussed, like it's 20 or 21, so that's totally fine, like 20, for example. Okay. All right. The student attaches the spring to the clamp as shown in figure 1.2. He hangs a 300-gram mass on the spring. Okay. Right. So we can see that that's the spring and he's attaching 300-gram of mass with it. Okay. He measures the new length L of the spring, and that is 53 millimeters. Calculate the extension E of the spring using the equation E is equal to L minus L naught. L is the new length that was 53. And the actual length was 20, so this gives you 33, and it's in same millimeters, so it's totally fine. Calculate a value for the spring constant K using the equation K is equal to F by E. Now the question is, where is the F? F is given here 3.0. If it's not given, you can convert it from W is equal to mg. So you can solve it now as per that standard. But as it's given, so 3.0 divided by extension, that was 33. Okay. So 3 divided by 33, it gives you 0.09 Newton per millimeter. That's totally fine. That was in Newton, that's in millimeters. Method 2. The student pulls the mass down a short distance and releases it so that it oscillates up and down. Figure 1.3 shows the time t taken for 10 complete oscillations. You need to underline that very important information. How many oscillations are there? 10. Record the time t taken for 10 complete oscillations, and it's easy to see from it 3.46 seconds. And you have to write exactly the same 3.46 unit is set. Calculate the time taken for one complete oscillation. That was the time for 10 oscillations. So divided with the 10, you may get 0.346 seconds. Right? Okay, that was the missing thing here. So that is 0.346 seconds here. Calculate t square. Now the t that you calculated here, take its square. So you will use a calculator for that. 0.346 here, that gives you 0.1197. 0.1197. And when you round it off, you make it easily like 0.12. And the unit will be seconds here. Okay. Calculate the spring constant using the equation K is equals to 0.040 m by t squared, where m is this. So 0.040 into 0.30 divided by t squared, that was 0.1. Okay, now that's a very important thing, even though that's a very simple and easy question. But if you find any difficulty, that is your wrong answer somehow, and you put the same answer here, so you may get easy 1 mark here as easy as error correct for. Okay, so if I do this here, 0.040 multiply 0.3 divided by 0.12, so you may get 0.10. The two values for k are the same within the limits of experimental accuracy. Okay, so where are my two values? The first value was it was actually 0.093 divided by 33, 0.0909, or you can say 0.091. Okay, the second value is 0.10. So what you do, like you divide, so subtract 0.91 and subtract the. That's a very important question. Like you have to tell either these two values are similar, same, or not. And how can you find out? Like you can find out first either they are in the limits of experimental accuracy or not. Like how can we work out? Like subtract both values, like larger minus smaller value, and then divide with their average. And the average is like zero point 0.1 plus 0.091 divided by 2, and their average is 0.09 0.09. Okay, so zero point 0.1 minus 0.091 divided by 0.0955. So I multiply it with 100 and I will get 9.42. Okay, and which is less than 10%. So if my working is here, you can easily say yes, the values are equal. Okay, or you can say like okay, 0.1 and 0.09 are very close together. Okay, so you can use the same. Otherwise, the values are considered to be equal as both are within limits of experimental level. And mention it here, like it was 9.42%, which is less than 10. That's important. Okay. A student states that repeating method 1 with different masses would improve the reliability of the values depend on K. Suggest additional values for the mass that you would use when repeating the experiment to improve the reliability. The value should be close to the initial value, and because the initial value for the mass that was 300 gram. And usually when you do this experiment, you may vary the values in a similar manner. For example, if I take 100 gram, then I change it 200 gram, then 300 gram, then 400 gram, then 500 gram, and so on. Okay, so these are the possible additional values that we should take in. Right. Okay, moving toward question number 2. That's also a very important question. Student determine the resistance of the resistance wire. She uses the circuit shown in Fig 2.1. Okay. You can see that there's a power supply here, and then there is the length of the resistance wire in between, and lighting contact and the ammeter connected. She measures the current I in the circuit, writes down the current reading shown in figure 2.2. Where figure 2.2 it is here. So this is 0.4, 0.5, 5, 2, 5, 4, 5, 6. This is 0.56. And it's written here If it's written MA or mu A, then you have to write milliampere or microampere. He places the sighting contact C at a distance of 20 centimeters from P. He records the potential difference across the length of the resistance wire. She repeats the procedure using the values 40, 60, 80, 100. The readings are shown in table. All right. So first of all, anything that is missing here, you need to complete. Right. That's a very important thing. You shouldn't miss it. And the values are here. Calculate and record in table 2.1 the resistance R of 20 centimeters for the resistance wire. Use equation V by I. Okay, so what was the I here? So the free circuit. So 0.56. Okay, so this is 0.605 0.5 0.6 0.56. This is 1.0714. 1.0714. So I may be writing 1.07 as there are three number of significant figures in this column. I should also write 3. Okay. Calculate and record this is done. Complete the column headings. This is already done. Okay. Look carefully at the values of L and R in table 2.1. Tick one box to show your conclusion from the results. You can see that when the length is increasing, the resistance is increasing. And okay, so it means that which answer like seems to be perfect here for you. Like R is directly proportional to length within the limits of accuracy. Yeah. Okay. R is not constant. R was increasing as the length. Justify your conclusion by reference to the results. Okay, and the results are here. Like for the 20, it was 1.07, for 40, 1.96, 60, 3.09. We can see that the length is increasing, the resistance is increasing. Okay, so you have to quote the results here. I'm just writing the statement as length is increasing, so the R. Okay. Use the values in table 2.1 to estimate the potential difference across 50 centimeters of resistance. Okay, right. At 50, it was missing. Okay, so you have to find out the value between 50, right? So that is very like easy one. You can work out that value. How can you work out that value? For example, first of all, you have to take the difference like between 3.05 and 1.96. Sorry, let's see again. It says estimate the potential difference, not the resistance. Okay, so it should be in between here, 1.71 to 1.10. So 1.71 minus 10.12. Why divided by 2? We have to take the difference 1.71 minus 1.10 and we got 0.61, and when you divide it 0.61 by 2 we got 0.35. Okay, like 0.31 you can say. So add this in this value, so you make it at 50 mark. So plus 1.10, you're at 1.405 or 1.41. Okay, so as the values are in 3 decimal places, so you have to write 1.41. Okay, complete the column headings. We already done it. Okay, sorry, this was here. 1.41. Calculate the resistance of 50 centimeters of the resistance wire using the equation V by. So use the values of current I from part A, give your answer to a suitable number of significant figures. that are given in the question. Okay, already given. For example, V E by I is 1.41 to number of three number of centimeters divided by I. So where is the I? We have already found out that here 0.56. Okay, so 1.41 divided by 0.56, 2.5, 179, or 2.5. Because the minimum number of centimeters is 2 in the question. Okay, so last question. In this type of experiment, it is sensible to keep the temperature of the resistance wire as close to the room temperature as possible. So just one simple way to minimize the rising temperature of the resistance wire. Okay, the best thing is that like use a thinner wire. When there is a thinner wire, so less resistance we offer. Okay, and use low value of current, you can say. Okay, lower current. And the very important thing that you need to remember it like switch off between the reading. And you have to pick the reading for the next reading when you're setting it or you're changing stuff, you have to off it. Okay. So that is most repeated one. Switch off between reading. All right. So with that, we have done one spring question and one resistance question. All right. Take care.